Welcome to my talk, Learning to Optimize Non-Rigid Tracking. This work is done as an internship project in the Visual Computing Group at Technical University of Munich. And also collaborate with the University of Tokyo. This work focus on the inter-frame non-rigid tracking task. To find the non-rigid motions between two partial scans from a commodity RGBD camera. Non-rigid ICP is a widely used method to solve this problem. It approximates the non-rigid surface motions by a deformable model called deformation graph. Given two RGBD frames, the nonlinear optimizer Gauss-Newton determines the graph parameters that minimize this energy function. Here the E-fit is the data fitting term that measures the closeness between the warped source frame and the target frame. The term E-reg is the regularization term. Many different data fitting terms have been proposed over the past decades, such as the geometric point-to-point, the point-to-plane, and color consistency constraints. However, these constraints only work when they are close to the solution. In the case of large motions, these constraints cannot provide convergent residuals and lead to tracking failure. In this work, we alleviate the non-convexity of this problem by introducing a deep feature alignment term which is learned end-to-end through the convolutional neural network. We assume that, by leveraging the large receptive field of convolutional kernels and the nature of the data-driven method, the learned feature can capture the global information which helps Gauss-Newton to jump over local minimums. We use a CNN to extract non-rigid features from the input frame. The deep features of the two frames are then aligned by a differentiable non-rigid solver. Finally, we apply the L1 loss on the translational vectors of the deformation graph. This pipeline is trained end-to-end. For network training, we use the non-rigid dataset from Bozic et al. 2020, which captures a variety of deformable objects including adults, clothes, and animals, etc. Annotation is done automatically by using our non-rigid tracking and reconstruction method. The long-term motions between distant frames can be obtained by accumulating small inter-frame motions through time and space. Compared to the classic NICP methods in Newcomb et al. And Zollhofer et al., our method manages to converge to the global solutions on large deformations. Our non-rigid solver has a nested loop structure, with Gauss-Newton to minimize the tracking objective in the outer loop, and Preconditioned Conjugate Gradient (PCG) to solve the Gauss-Newton update equation in the inner loop. For the positive definiteness of the system, solving the equation is equal to find the x that minimizes this quadratic form. Preconditioning speeds up the convergence of an iterative solver. The general idea behind preconditioning is to use a matrix, called Preconditioner, to modify an ill-posed system into a well-posed one that is easier to solve. The preconditioner has the potential to significantly speed up the solver by reducing the convergence steps. We argue that PCG converges much faster if the design of the preconditioner involves prior expert knowledge of this specific task. Then we raise the question: does the data-driven method learn a good preconditioner? Here, we propose the ConditionNet based on neural networks with an encoder and decoder structure to learn the preconditioner. ConditionNet generates a lower triangle matrix L from the original matrix. The preconditioner is computed as L by L transpose. The learned preconditioner is fed to a PCG layer to solve the linear system in a limited number of iterations. Finally, we apply the L1 loss on the predicted solution. To obtain the ground truth solution, the standard PCG is executed as many iterations as possible till convergence. We propose three variants of the ConditionNet with different densities: the ConditionNet dense, sparse, and diagonal. They are decided by the number of non-zero entries in the matrix. The curves show the average PCG convergence on the testing dataset. Our methods require 2 to 3 times fewer PCG steps to achieve the same residual than the baseline methods. Thank you for listening.